Welcome to this problem walkthrough. Today, we'll explore the challenging optimization problem titled Create Maximum Number. In this problem, we aim to generate the maximum number of length k from two arrays while preserving the relative order of elements. Let's dive into the details and break it down step by step. In this problem, we are tasked with creating the maximum number of a specified length, k, by combining elements from two given integer arrays, nums1 and nums2. The key requirement is that the relative order of the selected elements within each array must be preserved. This means that while you can pick elements from either array in any proportion, once you select an element from an array, the elements that come after it in that array cannot appear before it in the result. The final output should be a list of integers representing the largest possible number of length k that can be formed under these constraints. For example, if nums1 and nums2 contain digits from 0 to 9, and their lengths are m and n respectively, the goal is to use exactly k elements in total, where k is less than or equal to m plus n. Now, let's look at the input and output formats. The input consists of nums1, nums2, and the integer k. The output is a list of integers that represents the maximum number formed. This forms the foundation of the problem, and now we'll explore some examples to clarify this further. Let's consider the first example. Here, nums1 is 3, 4, 6, 5, nums2 is 9, 1, 2, 5, 8, 3, and k is 5. The task is to combine elements from nums1 and nums2 to create the largest possible number of length 5. To achieve this, we can select 9, 8 from nums2 and 6, 5, 3 from nums1. Notice that the relative order of the elements within nums1 and nums2 is preserved in the final result. Specifically, in nums1, 6 comes before 5, and 5 comes before 3, just as they do in the original array. Similarly, in nums2, 9 comes before 8. Combining these selections gives the maximum number 9, 8, 6, 5, 3. This example highlights the balance between selecting the largest digits and maintaining their relative order within their respective arrays. Let's now move on to the next example. In the second example, nums1 is 6, 7, nums2 is 6, 0, 4, and k is 5. The objective is still to create the largest possible number of length 5. Here, the optimal selection involves taking all elements from nums1, which are 6, 7, and combining them with all elements from nums2, which are 6, 0, 4. Together, this forms the maximum number 6, 7, 6, 0, 4. Once again, the relative order of elements from each array is preserved in the result. For instance, in nums1, 6 comes before 7, and in nums2, 6 comes before 0, which comes before 4. This example demonstrates how, in some cases, using all elements from both arrays can yield the optimal solution. Let's take a look at one more example to further illustrate this concept. In the third example, nums1 is 3, 9, nums2 is 8, 9, and k is 3. To construct the largest possible number of length 3, we choose the digit 9 from nums1 and the digits 8, 9 from nums2. This selection results in the maximum number 9, 8, 9. Notice that the relative order within nums1 and nums2 is maintained. In nums1, 9 appears after 3, and in nums2, 8 appears before 9. This example highlights how the solution can involve selecting a mix of elements in varying proportions from the two arrays to achieve the optimal result. Finally, there are some constraints and edge cases to consider. For example, if k equals the total length of nums1 and nums2, you must use all elements. When k equals 1, you simply return the largest single digit. If one array is empty, you take all elements from the other array. And in cases where all elements are identical, relative order must still be preserved. These considerations help ensure that the solution works for a wide range of inputs. Creating the maximum number of length k from two arrays is indeed a challenging optimization problem because we must maintain the relative order of elements while achieving the largest possible sequence. One approach we considered was the brute force method. Here, the idea is straightforward: generate all possible subarrays of length k from both input arrays, merge them while preserving their relative order, and then select the lexicographically largest result. However, the complexity of this approach is extremely high. Generating all combinations alone has a time complexity of O, m to the power of k asterisk n to the power of k, and merging these combinations further adds an O-K cost. This makes the brute force approach impractical for large inputs. To address this inefficiency, we turn to an optimized greedy approach. The key idea here is to split the k elements between the two arrays. For each possible split, we select the maximum subarray of the given size from each array using a greedy approach, merge these subarrays into the largest combined sequence, and keep track of the best result. The problem can be broken down into three main tasks: selecting the maximum subarray of a given size from one array, merging two subarrays into the largest sequence, and iterating through all valid splits of k. Let's explore these tasks in more detail. Selecting the maximum subarray from a single array is accomplished using a greedy approach with a stack-based method. This ensures that the subarray is as large as possible while maintaining the relative order of elements, and it operates efficiently with a time complexity of O(n). Once we have the maximum subarrays from both input arrays, the next step is to merge them into the largest possible sequence. This is done using a custom merge function that compares elements lexicographically while maintaining their relative order. The merging process runs in O(k) time, as we are essentially combining two arrays of size k. Finally, to account for all possible splits of k, we iterate through each valid division, where I elements are taken from the first array and ki elements from the second array. Combining these steps, the overall time complexity of this approach becomes O(k*m plus n, which is significantly more efficient than the brute force method. Additionally, an alternative dynamic programming approach was considered. This method would involve pre-computing solutions for selecting subarrays and merging them efficiently. However, the complexity of implementation and memory overhead makes dynamic programming less attractive compared to the streamlined greedy approach. Ultimately, we chose the optimized greedy approach for several compelling reasons. First, it achieves an acceptable time complexity of O(k*m plus n, which is manageable even for large inputs. Second, this approach is relatively simple to implement, as it breaks the problem into smaller, modular tasks, selecting subarrays, merging them, and iterating over splits. This modularity also makes debugging easier. Third, it is highly practical for this problem's constraints, as the greedy selection and merging steps are both efficient and effective. When comparing the three strategies, the brute force approach is clearly infeasible due to its exponential complexity. While dynamic programming could theoretically optimize redundant computations, its significant memory requirements and implementation complexity outweigh its benefits in this scenario. The chosen greedy approach strikes the right balance between efficiency and simplicity. However, it's worth noting that the greedy method may not generalize well to problems with additional constraints or different optimization goals. Still, for this specific problem, it is perfectly suited to meet the requirements. By focusing on core tasks, selecting subarrays and merging intelligently, we achieve an optimal solution within the given constraints. To understand this problem, the goal is to create the maximum number of length k using two arrays, while keeping the relative order of elements from each original array intact. This is a challenging optimization problem because it involves balancing the constraints of maintaining order and achieving the largest possible lexicographical result. The first step in solving this is to define a subproblem: how to extract the lexicographically largest subarray of a specific length, I, from a single array. To achieve this, we use a greedy algorithm with a stack. The stack helps us track the largest numbers while ensuring the order is preserved. As we iterate through the array, we use a systematic approach. If the stack is not empty and the current element is greater than the top of the stack, we consider removing the top element, but only if we can still form a subarray of the required length after popping. This process allows us to discard smaller, suboptimal elements in favor of larger ones. Finally, we truncate the stack to ensure it contains exactly I elements, if necessary, guaranteeing that the result is both valid and optimal for the given input. The reason this stack-based approach works so well is that it guarantees the lexicographical order by consistently choosing the largest possible numbers while adhering to the constraints. Once we've defined how to extract the maximum subarray from one array, the next step is merging two subarrays, one from each of the original arrays, into a single array of length k. The goal here is to ensure the merged array is also lexicographically the largest possible while maintaining the internal order of elements from each subarray. For this, we use a two-pointer technique. Starting with pointers at the beginning of each subarray, we compare the elements they point to. The larger element is appended to the result, and the corresponding pointer is advanced. If the elements are equal, we lexicographically compare the remaining portions of the subarrays to decide which one contributes the next element. This approach ensures that every decision made during the merge leads to the best possible outcome for the final array. By merging subarrays in this way, we ensure the resulting array is always optimal at each step. The next part of the algorithm involves iterating through all possible splits of the total length k between the two input arrays. This means we try every valid way to distribute k elements between the first and second arrays. For example, I elements can be taken from the first array, and the remaining k I elements must come from the second array. Not all splits are valid, though. For instance, if I exceeds the length of the first array or k I exceeds the length of the second array, we skip that split. For each valid split, we use the greedy algorithm to extract the maximum subarrays of the respective lengths from both arrays. These subarrays are then merged, and the resulting array is compared with the current best result. If the new merged array is lexicographically larger, it replaces the current best result. This exhaustive exploration ensures that no potential solution is overlooked, allowing us to confidently identify the global optimal result. There are several key insights that make this algorithm both effective and efficient. First, the greedy selection process, implemented with a stack, is the cornerstone for extracting the maximum subarray of a given length. It ensures that we systematically discard suboptimal elements while preserving the relative order. Second, the careful coordination between the two arrays during the merge step is critical. By comparing the remaining sequences lexicographically when elements are equal, we avoid merging in a way that could lead to a suboptimal result. Lastly, the combinatorial exploration of all valid splits of k between the two arrays guarantees that we exhaust the solution space, leaving no stone unturned. To implement this approach, we rely on a few key data structures: a stack for the greedy subarray extraction, 2 pointers for efficient merging, and an array to store the best result. Together, these tools allow us to navigate the problem space systematically and efficiently. Let's examine the complexity of this algorithm. The process of extracting the maximum subarray from a single array has a time complexity of O(n), where n is the length of the array. This is because each element is pushed and popped from the stack at most once. For merging two subarrays, the complexity is O(k), as each element is added to the result exactly once. When considering all valid splits of k, the algorithm iterates through combinations of the two input arrays, resulting in an overall complexity of O(k*)m plus n, where m and n are the lengths of the two arrays. Additionally, there are a few important edge cases to keep in mind. If one or both arrays are empty, the algorithm must handle this gracefully. If k exceeds the combined length of the two arrays, the problem constraints are violated, and this should be checked up front. Duplicate elements in the arrays can complicate comparisons, so the algorithm must still perform correctly in these scenarios. Finally, for very small arrays, care must be taken to avoid index errors. To solidify our understanding, let's walk through an example. Suppose we have nums1 equals 3, 4, 6, 5, nums2 equals 9, 1, 2, 5, 8, 3, and k equals 5. The first step is to try all valid splits of k, such as taking 0 elements from nums1 and all 5 from nums2, or 1 element from nums1 and 4 from nums2, and so on. For each split, we extract the maximum subarrays from both nums1 and nums2 using the greedy algorithm. These subarrays are then merged into a single array of length 5. After comparing all merged results across the splits, the lexicographically largest array is selected as the final result. In this case, the output is 9, 8, 6, 5, 3. This example highlights how the algorithm systematically explores all possibilities, applies the greedy selection and merging processes, and ultimately finds the optimal solution. This solution to LeetCode problem number 321, create maximum number, uses a combination of helper functions and a main loop to achieve the desired result. The goal is to construct the maximum number of length k by combining elements from two input arrays, preserving their relative order. First, the max subarray function extracts the maximum subarray of a given length k from a single input array. The algorithm uses a stack to build the subarray greedily, removing smaller elements when a better candidate appears, as long as the total number of elements removed doesn't exceed the allowable limit. Next, the merge function combines two arrays into the lexicographically largest array possible. It works by repeatedly choosing the larger leading element from the two input arrays until both are exhausted. The main part of the code iterates over possible splits of the length k between the two input arrays, ranging from max 0 k len nums2 to min k len nums1. For each split, it computes the maximum subarrays for the two parts using max subarray, merges them using merge, and keeps track of the overall maximum result. This solution efficiently handles the constraints of the problem and ensures that all edge cases, such as different input sizes and edge values of k, are considered. The time complexity is dominated by the combination of extracting subarrays and merging, making it suitable for the input size limits. Here, we start with the maxNumber method, which is the main function responsible for constructing the maximum number of length k from two input arrays, nums1 and nums2. The key idea is to iterate over all possible splits of the length k between the two arrays. For each split, we determine the maximum subarray of size I from nums1 and the maximum subarray of size k I from nums2 using the max subarray helper method. These two subarrays are then combined using the merge method to form the largest possible number. After merging, we compare the result with the current maximum number stored in maxNumber using the compare method. If the new merged array is larger, we update maxNumber. The method finally returns the maximum number array once all splits have been evaluated. The max subarray helper method is designed to extract the largest subarray of a given length k from an input array nums. It uses a stack-like approach to maintain the maximum elements while iterating through the array. The variable drop is used to track how many elements we can discard in order to meet the subarray size requirement. As we iterate over the array, we compare the current element with the top element of the stack. If the current element is larger and we still have the option to drop elements, we pop the top of the stack. This ensures that we keep the largest possible values while maintaining the order. Once the stack is filled to the desired size, the method returns the stack as the resulting subarray. Additionally, the merge method combines two arrays, nums1 and nums2, into the largest lexicographical order possible. By comparing elements from both arrays and taking the larger one at each step, it ensures that the final merged array is optimal. The merge method concludes by returning the fully merged array, which represents the largest number formed by combining elements from the two input arrays. To support this, the compare helper method is used to determine the lexicographical order between two arrays starting from specific indices. It iterates through both arrays, comparing elements directly. If a mismatch is found, it returns the difference between the two elements. If the arrays are identical up to the end of one of them, the method compares the lengths of the remaining portions to decide which is larger. This ensures that the merge and maxNumber methods can reliably construct the optimal result by always favoring the larger array or subarray at each step. To solve this problem, we start with the inputs nums1 as 3, 4, 6, nums2 as 9, 1, 2, 5, and k as 5. Our objective is to create the maximum number of length k by carefully combining elements from nums1 and nums2. The first step is to determine how to split the length k between both arrays. For every possible split, we take I elements from nums1 and ki elements from nums2, while ensuring the split is valid based on the lengths of nums1 and nums2. Here, I is 2, meaning we take 2 elements from nums1 and 3 elements from nums2. Next, we use a helper function max subarray to find the maximum subarray of the specified length from each array. Starting with nums1, we need a subarray of length 2. To do this, we use a stack to construct the subarray while ensuring the result is both of the required length and lexicographically maximum. Traversing nums1, we first push 3 onto the stack. Then, we encounter 4, which replaces 3 since it's larger and we are allowed to drop 1 element. Finally, we push 6, resulting in the maximum subarray, 4, 6. Now we move to nums2, where we need a subarray of length 3. Using the same max subarray function, we initialize an empty stack and calculate that we can drop up to 1 element while traversing nums2. We begin by pushing 9 onto the stack, as it's the first element. Next, we push 1, but since it's smaller than the elements ahead, it's replaced by 2 after popping 1, as this ensures we maintain the maximum possible subarray. Finally, we push 5, completing the subarray as 9, 2, 5. With the maximum subarrays from both arrays determined, the next step is to merge them into the largest possible number. This is done by comparing the elements of the two subarrays, picking the larger leading element at each step. Starting with 4, 6, and 9, 2, 5, we first pick 9, then 4, followed by 6, 2, and finally 5. This gives the merged result, 9, 4, 6, 2, 5. With the merged result, 9, 4, 6, 2, 5, we now compare it with the current maximum number, which is initially empty. Since our merged result is larger, it becomes the new maximum number. The final output for this example is 9, 4, 6, 2, 5. Moving on to the second example, we have nums1 as 6, 7, nums2 as 6, 0, 4, and k is 5. Again, we determine the split of k between nums1 and nums2. Here, I is 2, so nums1 contributes 2 elements and nums2 contributes 3 elements. Using max subarray on nums1 with a length of 2, we push 6 and then 7 onto the stack, resulting in the subarray 6, 7. For nums2, we need a subarray of length 3. Traversing through nums2, we push 6, then 0, and finally 4 onto the stack, resulting in the subarray 6, 0, 4. Next, we merge the two subarrays 6, 7, and 6, 0, 4 into a single maximum number. Starting with the largest leading elements, we pick 6 from nums2, then 7 from nums1, followed by 6 from nums2 again. Finally, we take 0 and 4, completing the merged result as 6, 7, 6, 0, 4. We then compare this with the current maximum number, which is initially empty. Since 6, 7, 6, 0, 4 is larger, it becomes the new maximum number. The final output for this example is 6, 7, 6, 0, 4. Now for the third example, we have nums1 as 5, 9, 3, nums2 as 8, 1, 7, and k is 4. Here we again split k, this time taking 2 elements from nums1 and 2 from nums2. Using max subarray on nums1 with a length of 2, we push 5 and 9 onto the stack. However, we replace 9 with 3 to ensure the subarray matches the required length and maintains its lexicographical order. This results in the subarray 9, 3. Finally, we calculate the maximum subarray for nums2 with a length of 2. By traversing nums2, we push 8 and then 7 onto the stack, resulting in the subarray 8, 7. Now, we merge the two subarrays 9, 3, and 8, 7 into the maximum number. Comparing the leading elements, we pick 9 first, then 8, followed by 7 and finally 3, forming the merged result 9, 8, 7, 3. Comparing this with the current maximum number, we find it is larger, so it becomes the new maximum number. The final output for this example is 9, 8, 7, 3. The time complexity of our solution is determined by 3 key operations: max subarray, merge, and the outer loop that iterates over different combinations of lengths for splitting nums1 and nums2. First, the max subarray function constructs a maximum subarray of a given length k using a greedy approach with a stack. For each element in the input array, we perform a push or pop operation, meaning the total work for this function is O, n, where n is the size of the input array. Since max subarray is called twice per iteration of the outer loop, once for nums1 and once for nums2, the combined work for this step during one iteration of the outer loop is O, n1 plus n2, where n1 and n2 are the lengths of nums1 and nums2, respectively. Next, the merge function combines two arrays, choosing the maximum elements to form the resulting sequence. Each comparison pops one element, and since we process k elements in total, the merge operation has a time complexity of O, k. Finally, the outer loop iterates over all possible ways to split k between nums1 and nums2. The range of splits is determined by the constraints max, 0, k n2, and min, k n1, resulting in up to O, k iterations of the loop. Now, combining these steps, for each iteration of the outer loop, max subarray is called twice, contributing O, n1 plus n2, and merge is called once, contributing O, k. This means the total work per iteration is O, n1 plus n2 plus k. Since there are up to O, k iterations of the outer loop, the overall time complexity becomes O, k asterisk, n1 plus n2 plus k. Shifting our focus to space complexity, this is determined by the auxiliary data structures used in the algorithm. The max subarray function utilizes a stack to store up to k elements, so its space complexity is O, k. Similarly, the merge function creates a new list of size k to store the results, also requiring O, k, space. Looking at the overall space complexity, the algorithm combines the outputs of max subarray and merge for each iteration of the outer loop but does not use any additional memory outside of these functions. As such, the total auxiliary space complexity remains O, k. To put this into perspective, consider a brute force approach. A naive solution would involve generating all possible subarrays of nums1 and nums2, merging them in every possible way, and comparing the results. This would result in a time complexity of O, n1 choose k1, asterisk, n2 choose k2, asterisk k, for each combination of k1 and k2, which is computationally infeasible. The optimized approach we are using avoids this by focusing on finding specific maximum subarrays and merging them efficiently. This brings the time complexity down to O, k asterisk, n1 plus n2 plus k, making it far more practical for larger inputs. Finally, let's analyze the best, worst, and average case scenarios for the time complexity. In the best case, where k is small compared to n1 and n2, the contributions of merge and the outer loop become negligible, simplifying the time complexity to O, n1 plus n2. On the other hand, in the worst case, when k is large and approaches the size of n1 plus n2, all components of the algorithm contribute significantly, so the time complexity remains O, k asterisk, n1 plus n2 plus k. The average case falls somewhere in between, depending on the relative sizes of k, n1, and n2. Mathematically, the dominant term in the overall complexity arises from the number of iterations, O, k, multiplied by the cost of the most expensive operations, namely max subarray and merge. This is why the final time complexity is O, k asterisk, n1 plus n2 plus k, with smaller terms becoming asymptotically negligible in the big O notation. When tackling this problem, there are several common mistakes to watch out for. First, not preserving the relative order of elements when merging subsequences can lead to invalid solutions. For instance, if we select elements greedily without paying attention to their original order in the array, we might end up with a sequence that doesn't adhere to the problem's constraints. A good way to address this is by using a helper function specifically designed to merge two subsequences while maintaining the relative order of elements. Another frequent issue is overlooking edge cases, such as when one or both arrays are empty. These scenarios can cause runtime errors or return incorrect results if not handled explicitly. To avoid this, make sure to check for empty arrays and consider cases where k is larger than the total number of elements across both arrays. Finally, generating all possible subsequences of length k from both arrays without any pruning can lead to exponential time complexity, making the solution impractical for larger inputs. Instead, leverage a monotonic stack to efficiently generate the maximum subsequence of length k for a single array, which simplifies the problem and improves performance. Another mistake to be mindful of is incorrectly handling duplicates. When arrays contain duplicate elements, it's easy to choose the wrong duplicate, leading to suboptimal results. To get this right, compare the remaining elements in both arrays when encountering duplicates to ensure you pick the lexicographically larger sequence. Additionally, ignoring time complexity can be a critical flaw. If the merge process for combining subsequences isn't optimized, your solution may fail for larger input sizes. To avoid this, consider approaches like divide and conquer or dynamic programming to eliminate unnecessary computations and ensure your solution is efficient. These optimizations not only improve runtime but also demonstrate a deep understanding of the problem to interviewers. From an interview perspective, there are a few key points to emphasize. First, optimization is crucial. Highlight your use of monotonic stacks to efficiently generate subsequences, as this is a technique interviewers often look for. Be prepared to explain the trade-offs between different approaches, such as brute force, greedy algorithms, and optimized solutions, discussing how clarity and efficiency play a role in each. It's also important to focus on maintaining lexicographical order when merging sequences, as this is a detail many candidates overlook. Make sure to clearly articulate how your solution handles this challenge. Don't forget to proactively communicate edge cases, such as empty arrays, scenarios where k exceeds the total number of elements, or arrays with duplicates. Finally, think modularly. Breaking the problem into smaller components, like generating and merging subsequences, not only makes your solution easier to explain but also improves its clarity and correctness. This problem shares similarities with several others, which can help you build a deeper understanding of the underlying concepts. For instance, problems like LeetCode 402, remove k digits, and LeetCode 316, remove duplicate letters, also involve constructing optimal subsequences while maintaining certain constraints. Exploring these related problems can enhance your grasp of techniques like monotonic stacks and lexicographical order. As for alternative approaches, brute force is one option. It involves generating all subsequences of length k from both arrays, merging them, and comparing all possible combinations. While this method is straightforward to implement, it's computationally expensive and impractical for larger inputs. A more efficient approach is to use a greedy algorithm combined with a monotonic stack, which allows you to generate maximum subsequences of different lengths efficiently. This method strikes a good balance between performance and complexity, though it requires careful handling of edge cases. Another alternative approach to consider is dynamic programming. By using a DP table, you can track the maximum subsequences for different lengths, which can provide a structured and systematic way to solve the problem. While dynamic programming can be more intuitive for some, it often requires more memory compared to the greedy approach with a monotonic stack. Choosing the right method depends on the specific constraints of the problem and your familiarity with these techniques. Each approach has its trade-offs, so understanding their strengths and limitations is key to crafting an effective solution and impressing interviewers. Great job making it to the end. To recap, we tackled a challenging optimization problem and explored how to use greedy algorithms effectively. Remember, practice is key to mastering these types of problems. Thanks for watching, and don't forget to like and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!